Strong password checker 2. Password is strong if it satisfies the following criteria. At least 8. 1 lowercase, 1 uppercase, 1 digit, 1 spatial character. So it does not contain over 2 same character in adjacent position. Okay, so just case by case. Now the first is a password. Password size is not greater than 8. Return false. And at least 1 lowercase letter. As 1 digit. Lower, upper digit. And at least 1 spatial character. Spatial. Password. We cannot have the same adjacent character. And digit will add about this digit. Okay, this word should be satisfied. Successful pairs of spells and potion. So you're given the 2 integer straight spells and potion of a length about m and n respectively, where spatial I represent the strength of I spells and potion represent the strength of I J potion. Okay, so you have a spell and potion, right? And also you're also given the success integer. A spell and potion pair is considered successful if the product of the strengths is at least success. So we want to know
你是不是没有分享到对的？
Okay, third person, persons n greater. Now we have a resource. How do we binary search? So for each spells, let's try to find what is the maximum index we can get. Quotient's size -1. Want to know the index. So me is going to be if you know x product about persons means is greater than success. What it means that we can update our maxima, right? And we can get more. We're gonna try to get more. Okay, more is smaller product because we started on descending. Small product. So r is being -1. So we'll get maybe 1. We add 1. For example, if we find about the mean is literal, we have 1 pairs. So we add 1. So yeah. Okay. It's time complexity and login. Oh, I forgot to convert the long. That's should be careful. Yeah, should be careful. Okay. Matching subsequent substring after replacement. Okay. You are given to string s and sub. You also given to the character array mappings. Remapping i's or news indicates that you may replace any number of old characters. This means okay, so sub means that mapping I or new indicates you may replace any numbers of old characters of sub with a new. Okay, any numbers of old. So we can say with a new, what it means new I or new I. New I is something number is more than once. What it means? We can make a substring of s by replacing 0 mode according to the mappings. Otherwise return false. Okay. So I want to replace the first element to E3 and T to the 7th. Now the sub is going to be L3, E3, E7. It's a substring of S. Oh, okay. So we can. You want to find substring, right? So substring, right? So the mapping. What is the mapping? Mapping is almost 26, or mapping level says 1000. Okay, and only have digits on lowercase and uppercase. Okay. So first we can replace the sub by mapping. and we want to make substring of s to make sub to substring of s, and we want to get true or false. What is the idea? So first thing you need to think about is that how to determine the substring. Yeah. Matching a substring. What should we do? We can say because the string length is 5,000, so we can use linear compare, right? But the problem is that we may replace many possible of the mapping, right? So we can mapping either it's going to be 3, t can going to be 7, and t is going to be 9. So well, what should we do? Okay, I may have an idea is that for each string or for each sub, if we cannot replace, that means we must split, right? If we can replace, for example, if we cannot replace, so what is I want to maybe you can use backtracking, but minimal. And one idea is that if the current string is not equal to sub, any sub open mapping, right? We can map at most once, right? So we can replace only can replace one. Okay, and you can replace one. So you can think as a graph. So I want to build a graph. So the graph is going to be character. This graph is going to be mappings. 0 will push back. Now, after we build a graph, we can try to we can try to actually you also need to efficient find about characterize. And characters at most, actually the graph of a node is at most, right? But I want to use our set to speed up the search. So what is the idea? Insert for each character. For each character, we want to try to find about Okay, let me think. Let me think about this. Okay, maybe I have no idea, but the time complexity, maybe if we can determine that if we cannot equal to any other not in the mapping substring, right? Substring J means we must move I. Otherwise, we can try to else we have two position, we have two transition. We can either move or not move, right? We can either move or we cannot move. So else we can either move I and J or move only I. So we have the dynamic programming approach. Let's say maybe we can use dynamic programming. DP is going to be subsize. Okay, snack one means it's not busy. DPIJ is that is the okay, so it's the so far to index I, and the current substring is matching to J, and can successful or not, can true or not. Yeah, so what should we do? Okay, so if it's not equal to subject, what it means? It means we must be mapping, right? So we must be mapping, right? So otherwise, okay, wait, what should we do? If we can move J only half. Can try to it's not negative one. We return research. And what's the edge case is that if J is equal to M, means we have matching success. Matching, right? Okay, if I is going to be 0. So what should we do? So we can jump I plus 1 if graph sub J is count about Si. That means we can move okay, or about self can move, right? So we can move. Wait a moment. True, false, true, right? So we'll get time complexity is going to be Wow, slow. Wait, I have submit or not? Mention space. Okay. Okay. Oh, wrong answer. Okay. Equal or why was wrong? Wrong mapping is going to be, we can replace any numbers of the old characters of as sub to new, right? Sub to new, yeah. So what I say? Yeah, so what is wrong answer? Because you have, wait, submit again. You say self, we must move I because we don't have string, right? And then oh, self equals secret 2. So what is this spells? A B C D E F G H I J K. We can map into sub count. Wait a moment. Oh, okay. We must be continuous, right? So we must be continuous means that this must be continuous, right? So this must be equal. Oh, wait, it's not dynamic programming. Actually, we don't need dynamic programming to do that. We can try to, for each, we just try to compare this four is the same or not, right? We don't need to do dynamic programming because this is not a subsequence, right? So, okay, that's absolutely wrong. Actually, each substring, we just compare if we can transform from sub to S, or this is the idea. 2. This is wrong because not the subsequence, right? So we just compare. Going to be So for example, say 4, 1, 2, 3, 4, right? So we can try to add 4. But we still need to build a graph. Okay. Still need to build a graph. Oh. Or we just try to use a mapping. Let's say graph. Yeah. So now in the mapping graph is going to be true. Now we try to do is for just no need to do anything, or graph we can replace to the string, also can get an answer, right? Wait, too slow. Not too slow. Okay. Graph. Okay. This is false, right? Because we cannot. Time complexity will be we get an answer. Actually, it should be correct because we don't. Is this a substring also? Yeah, but maybe TLE. But actually, I think this should be a set. Yeah. Oh, okay. Got it. Okay, and the count of subarray score less than k. That's important. So a score is a defined product of some length, for example, is its sign is length, right? Oh, okay. So what I want to do is, given about k, want to find about the numbers of the non-empty subarray whose score is strictly less than k. Oh, so well, the score is very simple. Find the number of subarray such that the sum product length is smaller than k, right? Smaller than k. What should we do? So we have two. What should we do? Score is going to be 6, right? Subarray, right? Subarray. Well. If we know the sub value is greater than 0, right? And this two values is increasing, right? So actually, I have a guess. We may use sliding window to do that. But this problem is how do we do? Well, how do we do? So I have a very simple idea is that for each position we can try to trace until the sum length is greater than k. We break. So brute force approach is, okay, think about brute force. Brute force is that enumerate. Brute force is enumerate each position. Try to extend until the sum is greater than sum and the product about length is greater than k, right? So yeah. So yeah, what is the idea? So idea is that if we know that this 2 value is greater than 0, must be greater than 0, because the sum of value k is values 1 to power 5, 10 power 5. Yeah. So we'll try to extend this. Why we just use 2-pointer approach, right? Or I have a 2-pointer approach. Pointers. So for edge, we just try to extend it, right? So we say but how do we shrink the product? 214, say 214, right? It's 214, right? It's wait, it's 214 35, it's 10, and we have this, so we try to product 3, 6. This is 3 and 6. R is going to be this. The product is going to be 3, 2 plus 1, 6. What should we do? If we know this should be 3 or is greater than 10, what should we do? Actually, it's very simple, right? So we can get a total sum and we can easily get a length. So we can get a sum, alright? So sum will add about our numbers are, and while sum product is greater than the k, means that 3 greater, right? 3 greater. So we need to sum minus about numbers out and plus, and we can add right? We can add this. For example, 2 we can have 2 and 1, right? And 4 we cannot do that. So we add about 1. We add about numbers 2. Wait. Why use length? It's going to be, so we want to make sure that the value is smaller, right? So we know that this range is always be smaller. So all the value, all the subarray from numbers R or subarray ending to R is smaller than K, right? So we can have R minus L at 1, right? So things make sense. 6 and 5. So yeah, the problem thing is this. Okay, accept. Okay. Okay. Waste too much time on problem 3. So let's go through this for problem. Okay, so problem 1 just a check problem. The problem say that we want to check that if this is strong password, and strong password you need to satisfy this for this criteria, many six rows. First, one at least 8 characters. So we just case by case, and then we just calculate that. Okay, if a lowercase we add 1, if this is the digit we add 1, if this is the uppercase we add 1, and if this is in the special character we add 1. And also when we go through the password, we can just try to check that if starting from a second index, we can check that if it's equal to the previous value, and return false. Now let's just try all condition is greater than 1, so it's positive. Yeah, so that's problem 1. And problem 2 is we want to find the success. The problem say you given to array spells and portions, and you want to find how many numbers of the portions that can be product smaller than the cells. So we can binary search the minimum. We can binary search the actually it's not the lowest index, it's the greatest index. Yeah, you want to find how many numbers of the portion that product is less than equal to, or at least success. And the idea is that for each spells we can binary search the portions, because the portions order doesn't matter, so we can sort by decreasing or descending. Yeah, descending. And then we just binary search the index that is greater than the success, and we sort by decreasing, so we can 5 we can easily find that. Okay, 2 is the lowest, the greatest index that is greater than success, right? So we will record index and we just add 1, we can get the numbers of the portions. Okay, so for example 1 portions is going to be, if we sort 1 to 5 4 3 2 1, and each value success is going to be 7. So each value binary search, and this we say okay, the product, okay, make you need to careful that the value is greater than the anti 30-bit 32-bit, so you need to make sure to convert to a long integer. to avoid overflow issue. So okay, say 5. What should we do here? We binary search versus left and right. Okay, we random guess about the mean, and then we see, okay, if the value is smaller, if that value is greater than success, that means we can guess more, right? Because the more the value is smaller, this is smaller, so we want to guess more, guess more, guess more until we are not success. The product 1 times 5 is more than success, so we break at this index, and actually the index should be here. Now numbers of the potions is 4, so yeah, because this is from 0, so we add 1. 0, 1, 2, 3, so we add 1. So if the index is 0, we add 1, it's going to be 1. If we cannot find about anything, let's select 1. Yeah, it's problem 2. And problem 3, let me understand problem first. Actually, it's very simple. You just try to find about just a string compare. Actually, it's you want to find about if we can mapping the sub to the string to make the sub as a substring of s. And my approach is that first we just use 2D array to record at the mapping. Mapping can be true or false, so we can make this to O1. And let's just try to find string compare. Just say, okay, if the string is the same, or we can mapping, continue, otherwise we cannot do anything. And we can find a substring, return food, return true, otherwise return false. Like time complexity is going to be as the size and sub size, time sub size, and it should be what's wrong time. Okay, so in C++, says okay, it's 8-digit, right? Okay, looks well. Okay, if this is 10,000, then we cannot use this approach, but okay, 5,000 we can just use brute force. And this problem is is that we want to find the numbers of non-empty subarrays such that the score sum product length is less than k. And you see the constraints, all the values greater than 0, so you can make problem simpler, because brute force is that we can enumerate each position, right? So we can, the time complexity is going to be n squared, but it's too slow. So we can try to do is, for example, we say if this value, we just try to use 2 pointer and maintain a left right pointer, and we just try to extend the right pointer. After that, we find until, okay, say this. Okay, you see this approach is that we add about the sum and the value is too big, we remove the value and we add the numbers of the subarray ending in R, so we can get our answer, because R is the, if we enumerate our ending position, and we can get a different numbers of the correct subarray that is smaller than k, because if the subarray, for example, if the subarray of this range is valid, that means this subarray is valid, and this subarray is valid, this subarray is valid, right? Also valid, is valid, is valid, is valid. So we just calculate the numbers of the distance, so we can get this 4. We don't need to brute force the L, yeah, because the value is increasing. It has the monotonic property, so we can do that. So that's today's test. And okay, this